subset of C. Again, we're not trying to prove this is always true. We're trying to show a particular example where this is true. For B, same thing. Pick two sets from the universe, A, B, where the complement of B and A is not the same as the complement of A and B. So show that the subtraction is not commutative. And then for C, pick two sets A and B such that their union is this entire universe, and their intersection is 0. And then show me what U minus B is, and make the observation that that's the same as A. So the point of this is just getting you some practice with these facts about sets and set operations by picking particular sets and actually working through what these statements say. So I tried to explain that in here. Give an example means show or describe exactly the contents of the sets, show what's on each side of the equal, and state whether the two sides are the same or not. All right, and then also do questions 6 and 8 from that section. So question 6, imagine U is an infinite universe. So it's some set containing an infinite number of things. And A and B are subsets that are also infinite. And then think about these questions. Would the complement of A have to be finite? Would the union of A and B have to be infinite? And would the intersection of A and B have to be infinite? And those are worth just kind of thinking about, trying some examples. You know, some infinite sets, the integers, the reals, for example. Play around with that, see what you think. And then question 8, I just want you to try and do the best you can with. So you're given a bunch of sets for students at a school. So D is the set of day students, M is the set of mathematics majors, and so on. And you're given the size of these sets, and you're also told that the number of day students who are math majors is 250, and so on and so forth. And using those facts you're given, see if you can figure out the answers to these 7 questions. And think about it in terms of set theory. And think about it in terms of what's the size of the union of two sets compared to the size of each set. And we looked at some of this on Monday. Mess around with it, see what you come up with. I'm not so concerned with, having the exact right number for each of these as I am seeing your process of getting there. So it's an exercise. And then the last question, 1.3, one question number 2, which is thinking about two sets. A is this set of 2 things, B is the set of 6 things. How many things are in their Cartesian product? And then try to come up with kind of a written description or interpretation of what the Cartesian product means. We know that it would be a set of tuples where the first element comes from here and the second element comes from there, but that's not meaningful to somebody outside the course. If you wanted to describe just kind of what the interpretation of this set is, what would that be? So again, think about that and see if you can find a sort of common sense description other than a set of tuples where the first element, et cetera, et cetera. All right, does that make sense? Again, we're just kind of working with these definitions and these operations, and we're going to talk more about unions and intersections and things like that. But you should have the basics that you need. So I also posted in the beginning of the homework section just a short little write-up on how to write up homework. I'm not too worried about this for PDF submissions, but having a consistent way of writing up problems and doing problems will be helpful to you, and it'll be helpful for me to grade it and such. Basically 5 guidelines for doing this. Try to do your homework as neatly as possible. If you make a mistake and you're working with pencil, you can erase it cleanly. If you're working in pen or it's a lot to erase, just draw a single line through it. Sometimes it's useful to see what you had and then decided not to use, because sometimes we think we've made a mistake and actually we were on the right track. So crossing out with a single line is helpful. For more complex problems, when we start getting into longer proofs and things like that, where we have to kind of trial and error our way to a solution, it's useful to sort of work this out on scratch paper first and then try to write up a nice clean solution to actually turn in. Um, so that's something to keep in mind. I strongly recommend working with pencil and paper. If you're really good and you have some really good technology for doing this with, you know, a tablet and a pen, you can do that. But I don't think anything is as efficient as pencil and paper. And there's a different mindset when you're working with something physical like that than when you're drawing on a touch screen, right? Um, so my suggestion is sheets of paper, good sharp number 2 pencil, nice eraser, and work from there. Try to write as neatly as you can. You're welcome to use lined paper or unlined or dotted paper, whatever you choose. Try to do your problems in order. So if you're working on questions 2 and 4 from 1.1 and then questions 6 and 8 and 9 from 1.3, do them in that order, right? There's times when I'm grading a homework and here's question 1, here's question 3, and there's no question 4. They jump to question 7, so they lose credit for question 4, and then maybe they come back to me later on and say, oh, question 4 was on the back. Okay. So I can grade it then. But do the problems in order. Number each problem, and make it clear what the number is. And when you get to the end, circle your answer or draw a box around it or somehow annotate it. These questions sometimes involve a lot of work and they have multiple answers throughout. Make it easier for me to find those answers and give you credit. Here's a suggestion for page layout. Again, this is more for when you're turning in physical paper, but it's perfectly fine for PDFs as well. Put your full name at the top, first name followed by last name, please. The course, the homework number, the date. Try to keep the left margin empty except for the problem number, so that if I look down your page, I can pick out the problems just by seeing what's in the left of the margin line. If there's multiple sections, you can do something like 5.2 or 5.2b and so on and so forth, but keep the rest of that margin clear. Work from top to bottom. So if you're working through a problem, begin at the top of the page, work your way down. When you get to the bottom, go to a new page. All right. Try to avoid, when you get to the bottom, going back up to the top and starting a second column, right? Or trying to write sideways in a margin because you ran out of space. Just go to a new page so that your whole homework reads from top to bottom, page 1, page 2, page 3, in a nice logical order. So that's the basic guidelines. The other thing is, if you're scanning your homework, make sure it's a reasonable scan. I don't need 1,200 dots per inch on scanning. And if you scan at a really high resolution, you get a file that's 20 megabytes. That's probably too much resolution. Canvas will choke on that and so on. So trying to find a balance between something that looks like an 8-bit game, and something that is really huge, 20, 30 megabytes. Make sure your scans are as clean as possible. So again, this is where working on like a nice clean sheet of paper that's not wrinkled up and stuff, and using a sharp pencil will get you a good scan. You can usually scan with a phone or a tablet. Adobe has scanning software that's free that works pretty well for multi-page stuff, or if you have a scanner, you've got that option. Again, I'm not going to be super dogmatic about this, but just take a look at the PDF you're uploading and see if it looks like it's going to be reasonable to ask someone to read it and grade it. If it looks reasonable, it's probably fine. All right. Any questions about any of that? All right. So let's get back into set theory. So we left off, I was talking about the complement of sets. And if we have, a complement inside another set, we start with that other set, we throw away the things in A. But when we just talk about the complement of a set, AC or A bar, we're basically starting with the whole universe, throwing away everything that's in A. So the complement of A is everything in the universe that's not in A. So if the universal set is 26 letters A through Z, and A is A-E-I-O-U, then the complement of A would be all the things that are not in A, right? So this would be the set of vowels, this would be the set of consonants. So kind of what you would hope we mean by a complement. All right, so I said we're going to do a lot of, for example, making new sets out of old sets. Um, and we'll come back and see more ways to do that. But we're also going to talk a lot about properties of sets, and in particular, properties of operations on sets. So we can think of these as set identities. And so for all of this, let's just let A and B be sets. And this means it doesn't matter what sets they are. They can be any sets at all. And the following are all true. Um, if we take A and we intersect it with the universal set, we get A. So reminder, U equals the universal set. So A intersected with the universe just gives us A. A union with the empty set also gives us A. So what if we take A and we take the union with the universal set? What do you think we get?
The universal set.
We get the universal set. Exactly, because this means give me everything that's either in A or in the entire universe. Well, that's the entire universe, right? That's what it means. And if we take A and we intersect with the empty set, what do we get?
The empty set.
That's the empty set, because we're asking for everything that's in A and also in this empty set. Well, there's nothing in the empty set, so the intersection is empty. So union or intersection with the universe acts like that. Union or intersection with the empty set acts like that. If we take A and we union it with itself, we get good old A. And if we take A and we intersect with itself, we also get A. What about the complement of the complement of A?
ZA.
Say again? I think I heard it.
Me?
Yeah, it's A because A complement is everything that's not in A. And so A complement complement is everything that's not in the set of everything that's not in A, double negatives, turns out to be A. We also have some, let me add C as another set in here. We also have some useful properties. A union B is the same as B union A. A intersect B is the same as B intersect A. And if we take A union the set B union C, that's the same as taking A union B and then unioning with C. And same for intersections. So this is called commutivity, or we can say the union and intersection operations are commutative. This is called associativity. The union and intersection operations are associative operations. We also have this. The complement of A union B is the intersection of the complements. And the complement of A intersect B is the union of the complements. So let me ask you a question. Does any of this look familiar to something else that you might have studied?
I think there was something similar. It was like engineering 250.
Yeah, Engineering 250 is digital logic, and we look at Boolean algebra and Boolean operations. And in that class, we talk about identities, and there's some similarity to what we're seeing here. Anybody remember what this pair of equations was called? It's a bit of a weird name. This was De Morgan's theorem. And De Morgan's theorem applied to Boolean operations. So if A and B were like trues or falses, A or B complement was A bar and B bar. And so it's almost like the union is taking the place of an or, and the intersection is taking the place of an and. And the universal set is taking the place of a one, and the empty set is taking the place of a zero. And if you think about Boolean algebra from Engineering 250, we had things like A and 1 equals A or 0 equals A or 1 equals 1, A and 0 equals 0, A or A equals A and A equals A. The double negation still works, not A is A. And De Morgan's theorem looked like this. And those are parallels to the set theory versions. And there's other things that follow from this. For example, if we take A union A bar, we get the universe. If we get A and we intersected with A bar, we get the empty set. And those correspond to A or A bar equals 1, A and A bar equals 0. So we're doing set theory, we're talking about set theory, but it's paralleling a lot of what we did with Boolean algebra. And that's not a coincidence or just kind of a random fact. Um, there's parallels between these because in some sense they're very much the same thing. The things we're doing with sets are very, very much the same as the things we do with Boolean operations. All right, so we have these identities. There's other identities as well. You can find tables of them in the textbook. Um, but these are useful sometimes when we have some, large expression involving sets and operations, and maybe we want to simplify it to some other form. For example, um, if I take a set A and I union it with A intersected with B, I claim I always get the set A back. And I'd like to know if that's actually true. I'd like to find a way to prove it. I'm going to have it later. Or you can put it out there. Um, so we have a mechanism we can use, which is called a membership table. And here's how this works. I want to prove that this set is the same as that set. Now, I could probably do this using some of my identities. I could show this is a subset of that, that's a subset of this, and then I could say they were equal. But there's a more mechanical way we can do this also. And that's to use this idea of a membership table. So here's what we're going to do. Imagine the universe of things is fixed. I don't know what that universe is. Maybe we're talking about integers or real numbers or animals at the zoo or something. But there's some fixed universe from which A and B come. And I'm going to make a table. And I'm going to make two columns, A and B. And I'm going to imagine I've picked some element from the universe. All right, I've got it here in my hand. This is one element from the universe. And I can ask the following questions. Is that element a member of A? And is that element a member of B? And whatever element I pick, I can answer those questions. It either belongs to A or it doesn't. It either belongs to B or it doesn't. And so I'm going to use a 0 to say element is not in the set. I'm going to use a 1 to say the element is in the set. So if I pick some element, maybe it does not belong to B, or maybe it does. And in either case, maybe it also does not belong to A, or maybe it does belong to A. And those are my only four options. Any element I think of in the universe, it might belong to neither set. It might belong to only B. It might belong to only A, or it might be in both. So one of these four situations applies to whatever element I picked. Now, let me make a column for A intersect B. And for something to be in this intersection, what has to be true? What does it mean to say that an element belongs to A intersect B? Just in plain words.
that it's in both sets.
It means it's in both sets. Thank you. If something is in the intersection, it's got to be in A and it's got to be in B. All right, so if I pick an element that's not in A or not in B, it's not in the intersection. If I pick something in B but not in A, that's not in the intersection. If I pick something in A, not in B, it's not in the intersection. But if the element I picked was in both A and B, then it's definitely in the intersection. And now I can make one more column for A union A intersect B. And so now I'm looking at this column and this column. For something to be in the union of two things, it has to be in either the first thing or the second thing. Well, in my first case, I picked something that was not in A, it was not in B. I found out it was not in the intersection. So it's not in this or that. It's not going to be in the union. And in the second case, it's not in A, but it is in B. It's not in the intersection. And so it's not in A, it's not in the intersection. It's not going to be in the union. In the third and fourth cases, the thing I thought of was in A, which means it's going to be in this union. And so in both of those cases, that would be a 1. So now I can take a look at this and I can take a look at this. And whatever element I started thinking about, if it's in A, it's also in A union A intersect B. And if it's not in A, it's not in A union A intersect B. And if it's in this set over here, which is in these two cases, it's also in A. And if it's not in this set over here, those first two rows, it's not in the set A. So any element I think of either belongs to both of these sets or belongs to neither. And that's our definition of saying this set and that set are the same. So that proves that this is equal to that. So that's one way we can demonstrate that an expression like this is true, is by using these membership tables. And I got to ask, does this look familiar to anything that you've done before?
It's like a truth table.
It's exactly like a truth table, right? That's really what it is. So all the stuff with truth tables kind of carries over to set theory, but we don't have to do K-maps, so yay for that. Um, but yeah, so this is just engineering 250 digital logic in a different form. All right, let's keep going. So, suppose you have a collection of sets. Suppose I have 5 sets. I'm just going to call them A1, A2, A3, A4, A5. So I could write the union of these like that. But we've got a shorthand for this. And it's kind of like the sigma notation that we talk about in calculus class. I can write a shorthand for this union by just saying the union from I equals 1 to 5 of A subscript I. So that's a shorthand for this expression. And I've got another shorthand I can use for the intersection, which would be the same idea. just the intersection from I equals 1 to 5 of A subscript I. So using that notation, we can start puzzling about some interesting questions. So here's an example. So I'm going to define a family or a collection of sets A subscript I to be the set of integers starting from I. And going up forever, where I is a positive integer. So that's my definition of each set, A1, A2, A3, and so on. So for example, A1 is just the set of integers starting from 1. A2 is the set of integers starting from 2. A3 is the set of integers starting from 3. And so on. All right, everybody good with those definitions? So let's look at operations we can perform on these. So suppose I take the union from I equals 1 to n of A subscript I. What do I get when I take the union of the first n of these sets? And if you're not sure, break it down. Let's start off with just A1 union A2. What does that equal to?
A1.
That's just A1, right? This is all the integers from 1 on up. Union the integers from 2 on up. That's just A1. What about A1 union A2 union A3?
Still A1.
Still A1. Is this making sense to everyone else? Right? We're defining an infinite collection of sets where each AI just looks like this. If I were to take the union of A1 through A4, right, I start with A1, I add stuff that's already in it, I add more stuff that's already in it, I add more stuff that's already in it, I'm still just going to get A1. So for any number n I pick, the union of these first n sets is just going to be A1. So what about intersections? What if I take A1 and I intersect it with A2? What do I end up with?
Oh,
A2? Right? Because I'm looking for the things that are in common between this set and this set. Well, it's just all the things in A2. What if I intersect the first 3 sets? What'll I end up with?
The last one.
Yep, A3. So if we generalize that and take the intersection of the first n sets, what should I end up with? Yep, AN. All right, getting the idea? So let's make it a little more challenging. Suppose I take the union of all of these sets. So going up to infinity means I want A1, union A2, union A3, union A4, forever and ever and ever. I want to take every set like this. There's an infinite number of them and glom them all together with a union. What should I end up with? A1, perfect. Because, all of these sets come from A1, so if I put them all together, I'm still going to get just A1. All right, last question. What about the intersection of all of these sets?
Infinity.
Say again?
A. Infinity.
There is no A. There's only A1, A2, A3.
I'm like A infinity. So like A and infinity.
So it feels like A infinity, but A subscript something, that something has to be a number. There really isn't an A infinity, but I know what you're thinking about, and conceptually that makes sense. But we're looking for an actual set. So it's something like A infinity. Ah, the nothing set. Right? This turns out to be the empty set. And that's a little weird, right? Because each of these sets is actually an infinite set. It's got an infinite number of things in it. But when we try to glom them all together, we end up with nothing. And up here, if I tried to take a billion of these sets and glom them together, I would get A 1 billion, which is an infinite set. It's all the numbers from a billion on up forever. But when we make this leap to saying, let's take the intersection of all of these, suddenly we end up in nothing. And that may feel counterintuitive, which I think it is. But we can argue as to why this has got to be the case. So suppose this intersection is not infinite. Suppose there's some number n, which is in this intersection. And maybe it's a really big number. Maybe it's 17 trillion and 5. But suppose there's at least one number in this intersection. Let's call that number n. Well, I know that n is not contained in the set A n plus 1, because this set is all the numbers starting from n plus 1. And since n is not in this set, it can't be in the intersection of this set with something else. Because to be in the intersection, it's got to be in every one of these, and it's not in this set. So I can't find any number that's in this infinite intersection. The intersection has to be the empty set. So that's just kind of a weird example of where when we make this transition from finite to infinite, sometimes things change, and they change in ways that may not seem like they make sense. And we're gonna explore that theme a lot in different topics in this course. So that's just a first pass at that. All right, let's talk about functions. So here's a definition. A function f And we'll usually write f colon a arrow b. This is a function from a to b. Is an assignment or a mapping from each element of A to an element of B. This is a big A. So a function from A to B is an assignment or a mapping from each element of A to an element of B. So if little a is an element of A, then we write f of little a for the element of B to which A is mapped. So in pictures, here's our set A, here's our set B, here's some element A, here's our function f. It maps that element to something we'll call f of A. And we can describe functions a number of ways. We could do it as a mathematical expression. We could do it with a picture. We could describe it in words. We could describe it in a C program, right? So for example, let f of x just be equal to x squared. And suppose a and b are each the set of integers. So here's a set of integers, here's a set of integers. And so the number 1 maps to the number 1. The number 2 maps to the number 4. The number 3 goes to the number 9. The number -2 also goes to 4. The number -3 also goes to 9. 0 goes to 0. Right? So these are sets of integers in this case. And to say we have a function f going from this set to that set just says everything over here gets mapped to something over there. All right, we can also describe a function using a set of tuples. So we can make a set of tuples to describe f. For example, the number 1 goes to 1, the number 2 goes to 4, the number 3 goes to 9, 0 goes to 0, -1 goes to 1, -2 goes to 4, -3 goes to 9, and so on. And I could make a very large set containing a bunch of these ordered pairs, and that set would describe my function f. We could also say, f of x equals x squared. That's a mathematical way to describe it. But this is an interesting way to describe a function as a set of tuples. because we talked about sets of tuples on Monday. And remember, we had a notion called the Cartesian product. And we said the Cartesian product was a set of all tuples, where the first thing comes from the first set and the second thing comes from the second set. So this set here that I've used to describe the function f of x equals x squared, this is just a subset of z crossed with z, the Cartesian product of z with itself. So this particular function is one element of this Cartesian product. If I had another function like g of x equals 2x, the way I could describe that as a set of tuples would be something like 1 comma 2, 2 comma 4, 3 comma 6, 4 comma 8, 0, 0, -1, -2, and so on. And that's also a subset of the Cartesian product of z with itself. So every function that I can write that maps from the integers to the integers is a subset of this Cartesian product. So if I just write this, the power set of that Cartesian product, this is the collection of all subsets of z crossed with z. So this one set here contains every possible function I can think of that maps from the integers to the integers. And if I do this, that's a set. That set contains every function that you've ever studied in mathematics. Every function from the real numbers to the real numbers. Sines, cosines, logarithms, squares, square roots, exponentials, all of that, they're contained in here. So this is part of why set theory is so powerful and so foundational, because a simple notion like this actually consumes a much larger concept, in this case, the set of functions. So set theory is a good foundation on which to build, which is why we start this course with it. There's a lot of other things will come out of it. All right, so suppose more generally we've got our function f. It maps from elements of A to elements of B. So we have some more terminology. A is called the domain of the function, and B is called the codomain of the function. If we have some element A, little a in the set A, f of A is called the image of A. And A is called the pre-image of f of A. So again, in pictures, here's our element A, here's f of A. So the image of A is just the thing that f maps to. The pre-image of this point is the thing that maps to f of A. And the range of f is the set of all f of A, such that A comes from the set A. Thank you. So the range of a function is the set of all the things that it maps to. So bunch of definitions, right? So suppose I have my function from the integers to the integers, where f of x is equal to x squared. So what is the range of this function? The range is the set of all things that get mapped to. So the range would be the set 0, 1, 4, 9, 16, 25, and so on. It's the set of things that are the image of something in A. It's making sense? All right, so we can talk about equality of functions. So suppose we have a function f going from A to B and g going from A to B. We can say f equals g, or just write it with an equal sign. This means the functions are equal everywhere. So f of x equals g of x for all x in the set A. So kind of what you would hope equality means. Two functions are equal if they have exactly the same value everywhere. And functions can be as bizarre as we like. For example, I could say f of x equals, let's say f goes from z to z. I could say f of x equals the rightmost digit of x. So f of 234 is 4, f of 14 is 4, f of negative 173 is 3, and so on. Or I could define a function to be the sum of the digits in x. Or I could define a function to be 1 if the number is even and 0 if the number is odd. I can define a function to be pretty much anything I want, as long as it satisfies the requirement that everything over here maps to something over there. And we do this in programming languages, right? I can say, integer f, parentheses, integer x. And I can say return 2 times x. That's a mathematical function. It goes from the integers to the integers. And the mapping that it follows is it takes an integer, multiplies it by 2. That's the function value. When you declare a C function and you list the types of the argument, you're listing the domain. And when you list the return value, you're specifying the codomain. So, I mean, we've been doing this since at least 121. But there's this more rigorous structure underneath. All right, do a 5-minute break, and then we'll come back and keep going with this. So let's come back at 107. All right, so functions are related to something called a sequence. So sequences could be something like, for example, 1, 2, 3, 4, 5. That's a finite sequence. So sequences are ordered, and this would also be a sequence: 1, 2, 1, 1, 2, 2, 1, 1, 1, 2, 2, 2. That's an infinite sequence. So if we want to make this more formal, a sequence is a function from a subset of C to a set S. For example, this sequence up here, this is a function f from, well, it's kind of uninteresting. It goes from this subset of Z into the integers. F of 1 is 1, f of 2 is 2, f of 3 is 3, and so on. This function goes from the set of positive integers into the set consisting of 1 and 2. F of 1 is 1, f of 2 is 2, f of 3 is 1, f of 4 is 1, f of 5 is 2, and so on. So these sequences are ordered. They're ordered elements coming from some set we can think of as S. And unfortunately, sometimes we use this notation of curly brackets. So we might say curly bracket AN to mean the sequence A1, A2, A3, and so on. That is not a set, though. It's a reuse of the notation of curly brackets. So this is not a set. We only have so many symbols, and so we reuse them for different things. Up to now, curly brackets meant we were listing a set, but here curly brackets mean a sequence. Okay, so why do we care about sequences? Let's look at some examples. Suppose I have a sequence where AN is equal to 1 over N and is an integer bigger than or equal to 0. So A1 is 1, A2 is a half, A3 is a third, and so on. So this is just the sequence 1, 1 half, 1 third, 1 fourth, and so on. And this is like kind of a discrete version of the reciprocal function. If we have the function y equals 1 over x, we can plug in any non-zero real number and we can find out what 1 over that is. Well, this is like the same thing, but it only has values for integer x's, right? So 1, 1 half, 1 third, 1 fourth, and so on. All right, so the reason that all of this is interesting or important is because of what we call a recurrence relation. So a recurrence relation for a sequence, let's say our sequence is just AN, is an expression describing the nth element in terms of the earlier elements. All right, and this is going to be a key concept. So a recurrence relation for a sequence is a way to describe the nth element of the sequence in terms of the earlier elements of the sequence. So let's look at some specific examples. So here's the sequence 1, 2, 3, 4, 5, 6, and so on. Sequence of consecutive integers. A recurrence relation would be something like this. The nth term is just 1 plus the n minus first term. So this formula describes this sequence. Says, hey, what's the seventh term going to be? Well, it's whatever the sixth term was. That was 6 plus 1 more. That tells me the seventh term is going to be 7. So this is a recurrence relation. This is a sequence. This is a recurrence relation. But suppose I had the sequence 100, 101, 102, 103, and so on. That's got exactly the same recurrence relation, right? The third term is the second term plus 1. So sometimes we also need to specify an initial condition, or maybe more than one initial conditions. Because if I'm told this is the relation describing the sequence, and I ask you, okay, so what is A3? Well, you know it's 1 plus A2, but unless you know what A2 is, you don't actually know what A3 is. And we kind of know what A2 is. A2 is 1 plus A1, but if we don't know what A1 is, we don't know what A2 is. And A1 would be 1 plus A0, but there is no A0 because we think of this first term as A1. So we need an initial condition, for example, A1 equals 1 or A1 equals 100. But that combination of an initial condition and a recurrence relation precisely defines that sequence. So questions about this, because this is going to be fundamental to this whole course. And CSE 222. We're going to keep developing it. All right, who can tell me a recurrence relation for this sequence? Yeah, you basically need both, or you have, well, you're missing some information if you don't have both.
AN equals AN minus 1 times 2.
Nice. AN equals AN minus 1 times 2. So the fourth term, 8, that's just the third term, 4, multiplied by 2. Perfect. And for an initial condition, I'll just say A1 equals 1, because that's the first term of the sequence.
I have a question.
Yeah. Mm-hmm.
And also the variance relation would be AN is equal to E. Jeez. I was gonna say 2 to the power N.
Ah,
I don't know if
so AN is also equal to 2 to the N.
yeah.
And that's what we call a solution to the sequence. That's a way that we don't have to use previous values of the sequence, right? It turns out an equals 2 to the, I think in this case it's actually n minus 1 if we think of this as term 1. And here it would be 99 plus n, and here it would be 0 plus n. So sometimes, yeah, we can find a closed form solution for the elements of this sequence. Awesome. Anybody recognize these numbers? 1, 2, 6, 24, 120, 720. So you're familiar with factorials? So this is just 1, this is 1 times 2, this is 1 times 2 times 3, this is 1 times 2 times 3 times 4, and so on. So here we're describing an is just n factorial, the product of the first n integers. But we could write a recurrence relation. A sub n is just n times a n minus 1. And our initial condition, a1 is equal to 1. All right, sort of makes sense. All right, so we'll be coming back to this idea of recurrence relations and initial conditions a few different ways throughout the course. And like I say, it'll be pretty foundational to a lot of what we do in here and what we do in some of our programming courses. Let's see, summations. So this is another shorthand kind of thing. Suppose I have a set of numbers, and let's say they're am plus 1, am plus 2, and so on. And suppose I want to add them together. Up to some number a subscript k. So I have a shorthand for this, which looks like that. And you should have seen this in other classes, right? This is just a shorthand for saying, okay, set I equal to m. Let's write down a subscript m. And then increment I to m plus 1, and this is a m plus 1. And then increment I again to m plus 2, this is m plus 2. And keep going until I is equal to k, that's a subscript k. So this is a shorthand way of writing that. Is everybody familiar with that summation notation? Yay, calculus. All right. And in programming, this is just a for loop, right? I could have a sum that I initialize to 0, and I could say for I equals m, I less than or equal to k, I plus plus, sum equals sum plus a subscript I. So this maps to what we do in computer science. Sometimes we might write it as the sum for m less than or equal to I less than or equal to k. So that would be legal also. And this choice of I, this is basically arbitrary. I could also write this as the sum for x equals m to k of a subscript x. Is that exactly the same thing as this? Absolutely. This is just an index variable. And just like when you do a for loop, where I go I equals 0, I less than 10, I plus plus, and I do something with I inside. Well, if I call that j, my function's going to do exactly the same thing. It's really just kind of a placeholder. So let's imagine a function that takes integers and gives us back some value. And suppose I say I want the sum from I equals 1 to 10 f of I. Okay, that's the same thing as saying I want the sum from x equals 1 to 10 f of x. Everybody okay with that? We can change the variable. I could also do this. I could do the sum from I equals 0 to 9 of f of I plus 1. So how do we break apart something like this summation symbol? Well, basically, do a for loop in your head or on paper. Set I equal to 0 and write down f of 0 plus 1. Set I equal to 1, write down f of I plus 1. Set I equal to 2, write f of I plus 1. All the way up to and including 9, f of 9 plus 1. And then just add these together. So this is f of 1 plus f of 2 plus f of 3 plus f of 10. And if I do that up here or over here, I'm going to get exactly the same expression out. So we can change the index variable. We can also change the limits of the summation as long as we adjust what we're doing inside appropriately. All right, and then we've got some useful properties with these summations. Suppose I have the sum from I equals 1 to 5 of 2 times f of I. So if I write it out like this, set I equal to 1, this is 2 times f of 1. And then add, if we set I equal to 2, 2 times f of 2. And then if we set I equal to 3, 2 times f of 3, and so on. So we get this. Well, since each of these is multiplied by 2, I can pull that 2 out like this. And if I want to save ink, instead of writing all of this out explicitly like this, I could just say the sum from I equals 1 to 5, f of I. So this is the same thing as that. And what did I do? Well, I took that constant 2 and I pulled it outside the summation. And so we have this general rule. Sum from I equals A to B, f of I times some constant is just a constant multiplied by that summation. And more generally, the sum from I equals A to B of K times f of I plus J times G of I. We can break this. Well, let me write it more simply. The summation of f plus g is the same as just doing those summations separately. Like that. And then if these are multiplied by constants, I can pull the constants outside the summation. So we can break these things up into smaller pieces. And do those look familiar from some other class you've done? This idea of pulling the constant outside the summation.
I was gonna say kind of like integration, something like that.
Exactly. Yeah, this is integral calculus. We have this notion that if you're integrating the sum of two functions, you can integrate them separately and add those together. And if you're integrating a constant times a function, you can pull the constant outside. Why does that work? Because integrals are just summations, right? They're infinite summations, but they're really just a summation. So they're using these facts in order to get those handy rules for simplifying integrals. So you've seen this before, just in different forms. All right, last thing to talk about with summations. We can nest these. So, for example, suppose I want to do the sum from I equals 2 to 4 of the sum from j equals 3 to 5 of I times j. And you see a homework question or a test question, you're asked to calculate this. What do? Don't panic, okay? Break it down into pieces. So forget about this summation in here. Let's just put some parentheses around this. And if we ignore what's in there, this is just a sum from I equals 2 to 4 of something. Right? Well, we know how to do that. Set I equal to 2, figure out what this is. Set I equal to 3, figure out what this is. Set I equal to 4, figure out what this is, add them together. That's all you got to do. So go slowly and confidently and don't look too far ahead. If I is equal to 2, what is this? It's the sum from j equals 3 to 5 of 2 times j. If I is equal to 3, what is this thing in parentheses? It's the sum from j equals 3 to 5 of 3 times j. And if I is equal to 4, what's this thing in parentheses? It's the sum from j equals 3 to 5 of 4 times j. And we're going to add them together. So if I can do this, I've got the answer to that. Well, I can do each of these because it's just a simple summation. So what does this say? Well, set j equal to 3. This will be 2 times 3. Set j equal to 4. It'll be 2 times 4. Set j equal to 5. It'll be 2 times 5. Add them together. That's what that thing's equal to. And so on. So when we nest things, whether they're summation symbols or propositions, when we get to propositional logic, we can break them down into pieces like this. And this is one of these cases where we don't want to think too far ahead about logically, what does this mean? We can just kind of mechanically follow through the definitions and say, okay, well, let's just evaluate this for I equals 2, 3, and 4 and add them together. And just kind of blindly do that. There's 2, there's 3, there's 4, add them together. And now, do the same thing to calculate what each of these sums is, and you get to your answer. All right, there's other ways that we might see summations represented. For example, if I want to do A1 plus A2 plus A3 plus A4 plus A5, I could say let S equal the set 1, 2, 3, 4, 5. And I could say let's do the sum over I as an element of S of A subscript I. This is an S, not a 5. So it's saying for each element in this set, let's do A subscript that element. And so this says, do A1, A2, A3, A4, A5, add them together. So this is like a for each or a for in statement in Python or in Java, right? Where we say, here's a collection of things, and for each thing in that collection, let's go ahead and do some operation. But this is more useful sometimes than specifying a range, because our range may not be, from one integer to another. They might be things that come from something more abstract like a set. And we can also do something like a sum from I equals 1 to infinity, or a sum from negative infinity to 0, or even a sum from negative infinity to positive infinity. And infinity is not a number, but this basically means keep going forever. Don't stop. So do it for I equals 1, 2, 3, 4, 5, and just keep going forever and ever and ever. Of course, if you add an infinite number of things, there's a good chance you're going to get an infinite sum, but sometimes you don't. For example, if I were to do the sum from I equals 1 to infinity of 1 over 2 to the I, well, that's 1/2 plus a quarter plus an eighth. And that does not blow up. That gets closer and closer to the number 1. So sometimes this makes sense, sometimes it doesn't. If I just do the sum from I equals 1 to infinity of I, that gets bigger and bigger and bigger. It doesn't have a numeric value. So we would say the sum is infinite. All right, and then the last concept related to that is the idea of a product. So if I say the product, this is an uppercase P for product instead of S for sum. The product from I equals 1 to N A sub I. This is just take A1, A2, A3, all the way up to AN, multiply them. So exactly the same as a summation, but you multiply instead of adding. All right, last topic for this unit, matrices. So how many people here have taken or are currently taking Math 215?
I'm currently checking out. Wait a minute.
Okay.
Yeah. Yes, I'm taking
Yeah,
Math 15.
cool. So a number of students. All right, so Math 215 is called linear algebra. Um, and linear algebra is like three different topics. It's the study of systems of equations. It's the study of usually higher dimensional spaces, and it's the study of matrices. And they're all the same thing. They're interchangeable. And a lot of what linear algebra discovers is the connections between these three seemingly different notions: simultaneous equations, matrices, and higher dimensional spaces. Um, so we're not going to get into a lot of detail on matrices because Math 215, you spend a lot of that just studying matrices, working with them, interpreting them, and so on. But we'll have a bit of occasion to do a bit with matrices in here. So I want to just kind of go over very briefest aspects of matrices. Um, and you'll get this a lot more, or if you've done 215, you've already seen this. So what is a matrix? Roughly speaking, it's big parentheses with some numbers inside. Okay, that's the worst definition ever given for a matrix, but that's what we can think of it as: parentheses with some numbers inside. This would be a 2 by 2 matrix, 2 rows, 2 columns. This is a 2 by 3 matrix, 2 rows, 3 columns. And the things in here, I'll usually write them as integers, but they could be real numbers. They could be complex numbers. They could be functions. They could be other matrices. They could be pretty much anything we want. But for here, we'll just think of them as just being numbers. And if we have, say, a pair of matrices, and they have the same number of rows and columns, we can define something like addition. And so if I want to add these two matrices, I do the simplest thing I could imagine. I just go element by element. 4 plus 3 is 7. 6 plus 5 is 11. -1 plus 6 is 5. And 2 plus 7 is 9. There's my addition. If I wanted to subtract two matrices, I would just do subtraction. 4 minus 3 is 1. 6 minus 5 is 1. And so on. So addition, subtraction, pretty straightforward. If I have a matrix and I want to multiply by a single number like 5, that's just adding this to itself 5 times. So I can just multiply each element by 5. And that's pretty straightforward. I can also have the transpose, which I just write a little t up at the top of a matrix. That means transpose it, swap the rows and columns. So first row, second column becomes second row, first column. Second row, first column becomes first row, second column, and so on. So we just kind of flip it around a diagonal. All right, so that's all pretty straightforward and intuitive. Addition, subtraction, multiplication by a constant, or transposing the rows and columns. What gets weird with matrices is when we talk about multiplication. So for example, if I want to multiply two matrices, we don't do the obvious thing. which would be 1 times 2 is 2, 2 times 3 is 6, 8, and 20. That doesn't work for us. We can do that, but it turns out not to be very useful. So multiplication of matrices turns out to be a little more complex. And I'm not going to ask you to do this on homeworks or exams, but like I say, you'll see this in Math 215. Let me just explain to you how this works. Basically, what we do is we take the first row and the first column, and we do what's called a dot product. So we would say 1, 2 dotted with 2, 2. And for this first row, second column, we're going to take the first row and we're going to dot it with the second column, 3, 4. And then this element down here would be 4, 5, dotted with 2, 2. And this would be 4, 5, dotted with 3, 4. Well, what is this dot product? This is from physics. If you've done physics, when you have vectors, you take their dot product to find out how a force in a certain direction contributes to motion in a different direction. If you haven't done physics, don't worry about it. But what do we mean when we say AB dotted with XY? It's just A times X plus B times Y. So multiply the first things, multiply the second things, add them together. So in this case, what we would get is the following. 1 times 2 plus 2 times 2. So multiply the first, multiply the seconds, and add them. Here we're going to multiply the first 1 times 3, multiply the seconds 2 times 4. Here we're going to multiply the first 4 times 2 plus 5 times 2. And here 4 times 3 plus 5 times 4. And then if we actually do the calculations, this is 2 plus 4 is 6, 3 plus 8 is 11, 8 plus 10 is 18, and 12 plus 20 is 32. So this is what we get when we multiply these matrices together. Why do we do that? Because it turns out to be useful for reasons that we're not going to worry about in this course. But this turns out to be a useful way to describe multiplication. And it turns out we can't divide matrices. There's no general way for doing division. So this is multiplication. But to say I want to take this matrix and divide by that, we don't have a general way of doing that. But we have something almost as good. We can take A and we can multiply by what's called the inverse of B. So this is like A divided by B. Because, if you want 2/7, you can take 2 and multiply by 1/7. And that's like taking 2 and dividing by 7. The trick is, what does this inverse mean? So B inverse is a matrix such that when you multiply by B, you get something like 1. We don't actually get 1, we get a matrix. So this matrix I, this is called the identity matrix. And it's basically it's a matrix with 1s along its diagonal and 0s everywhere else. So if I wanted the inverse of this matrix 2, 3, 2, 4, it would have to be some matrix such that when I multiply it by 2, 3, 2, 4, I get this. All right, what's the punchline of all of this? All the stuff we do in algebra with integers or with real numbers, we can do with matrices. We can define a set of matrices. We can define addition, subtraction, multiplication, something like division. And we can talk about properties of matrices. But one interesting property is that multiplication is generally not commutative. The way I defined multiplication, if I were to do this matrix times that matrix, I'm going to get a different result. So matrices break some of our kind of intuitive understanding of how operations work. But it turns out matrices are really useful for solving systems of equations. So depending on when you took CSE 120 and who you took it with, you may have studied Kirchhoff's voltage law and Kirchhoff's current law, KVL, KCL, for analyzing electrical circuits. And when you do this analysis, you end up with a series of equations, maybe 3 equations with 3 unknown voltages in them. And if you can solve those equations simultaneously, find values of those unknowns that make all 3 equations true, then you found the voltages in your circuit. And we can use matrices to solve systems of equations. We won't do that in here. When I taught 120, we went over how to do that using MATLAB or a similar tool. So you may or may not have seen that before. But matrices turn out to be one of the most useful ways to solve problems. And computers are very good at working with matrices. Doing these kinds of calculations is tedious for humans, but this is something a computer can do very easily. Right? I mean, these are just, repeated summations of things that we pull off with indices. What computers have a hard time with is finding inverses. And there's mechanical ways we can do that, but they're very, very slow. And the faster you can find inverses, the more you can do with these kinds of problems. And these problems pop up in finance and in game theory and graphics and all kinds of things. So matrices underpin a lot of what we end up doing in computer science, which is why CSE Math 215 is part of the CS sequence. All right, so not a lot of take homes for that as far as exams, right? Just think of a matrix as a collection of numbers, and there's ways to define operations on them. That's kind of all you need. That does it for our first unit. So you've got the problem set to work on. Strongly suggest working on that before Monday. And then Monday, come to class with questions on that first homework. We can talk about those in detail. And then you can finish those up, turn them in on Wednesday, a week from today. Monday, we're going to start talking about propositional logic. That's chapter 1 in the textbook. And that's going to be our next major unit. All right, cool. That's all I got for now. Have a good rest of the day, and I will catch everybody next time.
Thanks. Have a good day.
Thanks, you too.